In senior high school, STEM students are faced with dealing with the fundamentals of calculus. They seem to struggle with it and memorize its lessons as a bunch of formulas and not as a concept to understand the foundations which makes the universe. As such, this can be a turnoff to students aspiring to work in the field of STEM, and a scary subject viewed from other fields not involved in science and mathematics. However, with a change of perspective, calculus presents itself to be very simple. What we hope is that by the end of this film, you can see the great beauty and simplicity that is calculus. The first step towards seeing the simplicity in calculus, or in any other part of mathematics, is to go beyond the techniques and the symbolic manipulations and see the subject for what it is. To begin, when we graph something, we are always showing a relation between the variables plotted on the different axes. In effect, we can say that y equals f of x, where f is some function. For this demonstration, we are using the function f of x equals 1/3 x minus 2 raised to the second power. One, and only one, curve will be used for the whole film. Its purpose and meaning will change as we go by, but the curve will remain the same and between the same points. Point P1 with the coordinate x1 and y1, and point P2 with x2 and y2. When we input an x, let's say 6, the function will produce an output of f of x, for which in this case will result in a 0. Following this, if x is 12, then f of x will be 4. We graph the points using the information we have from 6 to 12. If we graph all the points all the way from 6 to 12, it'll form a line given all of the set of x's as seen. Anyways, we all know that the 2 points form a straight line, and the steepness or inclination of the line is given by, or more specifically, the slope, the change in y over the change in x. This is simple. If we use the coordinates from P1 and P2 to use for the slope, we'll get that m is 4/6. Plotting this secant line along the curve looks like this. The line we've just drawn connects the 2 points. We call this line a secant line, as it intersects the function in at least 2 points. Now, what the slope means is that every time the function f of x goes 6 units to either left or right, the function will go upwards for 4 units. That's what it means to have a particular steepness to a graph. However, this doesn't really apply for all of the points of a graph f of x. If we were to use a different set of points, say from x equals 14 to 20, it will result in this. The steepness or slope will become different. The secant lines are different, so we cannot really conclude that its slope is exactly 4/6 for every number we graph. It will result in varying values of the function and different slopes. Is there a way we can make a slope that's a one-size-fits-all for every value of x? Well, that's where calculus comes in. Going back to our starting graph, let's try to rewrite the slope formula we have earlier. We're taught that the slope is the change in the function delta f of x over change in x delta x. To visualize, to make a one-size-fits-all slope, we can plot a point P3 in the middle of the graph. This shortens the slope and makes 2 lines within the given set of x. We can see that delta x becomes smaller. We make them 3, we make them 4, and on and on. As we increase the number of points, we are essentially increasing the number of secant lines between x1 and x2, and we decrease the distance between 2 adjacent intermediate points. As we put as many points as we want, the delta x just gets smaller and smaller. We almost reduce the delta x to almost 0. We say almost because if delta x is exactly 0, it will be undefined. If we write down the slope with this concept, along with putting y2 equals f of x plus delta x, and y1 equals f of x, we get the following. Remember, we can plug in 0 to delta x, but with the help of calculus, we can say it differently, or instead of delta x being very close to 0, but not exactly 0, we can denote the slope as approaching 0. In a fancier notation, it's written as, this is what the concept of limit really is. We say that it's approximate because the slope can be made as many and as small as it can be, but remember that delta x can't be 0. They are merely approximations, but if we take the limit of the approximations exactly, the one-size-fits-all slope. This one-size-fits-all means the tangent line of the function, where it touches the line at exactly 1 point. It's awkward to write all of that limit notation, So to make things easier, we define the tangent line of a function as, also known as the derivative. If derivatives answer the question of what is the slope of a curve, then integrals answers the inverse of that question, which is what is the area under the curve. This is why integral is commonly called as an antiderivative, because it essentially asks the question, what function, when derived, gives our given curve function. Let's use the graph we used earlier. And this time, you want to find the area under the graph from x equals 6 to 12. To find the area under the graph, we can use rectangles to approximate the area. We know that the area of a rectangle is height multiplied by its length, which corresponds to the y-axis and x-axis, respectively. From x equals 6 to 12, the length intervals of the rectangle is 6 units. And we will be using the notation dx as to approximate instead of the conventional delta x, and its corresponding f of x values for the height. This will become apparent later. For now, we end up with the graph. As you can see from the graph, the area can definitely be calculated by this method, but there are large sums of errors we have to account for. Like the derivatives, we can make better approximations by making the rectangles smaller by making dx smaller. Let's use intervals of 3, which is half of 6. As we add more rectangles, the approximation improves. The trend is clear. As dx becomes smaller and smaller, the rectangles in turn also become smaller, thus requiring more rectangles to fit into the curve, resulting in an even more precise approximation of the area. Eventually, using a very small value, we might as well be equal to the area under the curve. So how would we add all these rectangles together to find the area? When we have a dx that's so small, we are bound to have hundreds or even thousands of rectangles. How would we even add them all? The solution lies in what we already know from algebra. Do you remember how we would sum all the values in series back in the algebra days? By using the sigma notation. But in calculus, instead of using the sigma notation, we use the integral symbol. The reason being is that we are dealing with infinitesimal continuous measurements instead of finite discrete values. Basically, everything else applies. The lower limit is represented as a, while the upper limit is represented as b. And now for the big question. What are we summing up? The rectangles, right? So what's the formula for a rectangle? Length times height. What's the length of the graph? Dx. And what's the height? F of x. Therefore, we get, which is basically the calculus version of a sigma notation. We can read this expression as the sum of f of x times dx in the domain of a to b. We don't use sigma notation here because it is not in any particular discrete sum for any choice of dx. Rather, the integral notation indicates what that continuous sum will approach as dx approaches 0, which is the area under the curve. It shows that integral is the inverse of a derivative. You can even prove that integral is the inverse of a derivative algebraically. Take dA, which is the small portion of the area of the curve. The length of dA is dx and the height of dA is f of x. So dA is equal to f of x times dx. Dividing both sides by dt yields dA over dx equals f of x, which is the derivative. Calculus has its applications everywhere around us. For instance, calculus can help flatten the curve of disease outbreaks, much like the occurring coronavirus pandemic. It gives us deep insights and can formulate a model to compute and predict the spread of the virus and how data can help lessen the spread and flatten the curve. Calculus is used in the development of many scientific inventions and discoveries in the field of engineering, physics, economics, chemistry, and more. Through approximations, we can get answers to any question we have, and through calculus, we learn that everything makes sense once simplified.